Okay, so when we talk about equilibrium, we're talking about reactions that can happen both forward and backward. So you will always see an equilibrium reaction as being written with your reactants, and then your arrow to form a product is always going to be a half arrow with a forward and a backward, because it means that this reaction can go this way, and then this can also go backwards and decompose into that. The equilibrium will sit where you will add some reactants and they will react to make products until for every one that joins together to make that, one of those breaks down and makes that. So the reaction levels off and happens both forward and backward at the same time, at the same rate. So that is where the position of the equilibrium sits. So in order for equilibrium to occur, the one thing that we have to have is a closed system, okay? Because none of these things can escape, because otherwise it won't reach equilibrium. So if it is in a closed system and this reaction is dynamic, and when we say the word dynamic, we mean it can happen in the both forward and backward reaction. So it's continuously reacting, then it can reach equilibrium. So what you would see, for example, in a graph, is that we would add a certain amount of reactants at the beginning of the reaction, because they're going to have a high concentration up there. At the beginning of the reaction, there's going to be no products because we haven't made them yet. So then the reactants are going to get used up. So their concentration is going to decrease, while the products are getting made. So their concentration is going to increase up until a certain point. And that point is where these reactions level off, because that means that at this point over here in time, every reactant that gets used up, one also gets made. So these points here, where it's level off, that is the point where equilibrium has been reached, because now they're straight, meaning the concentration is not changing, because for every one used, one is being made on both the reactants and the products. So you'll always see that same shape in a graph. Of the reactants would decrease till they get to a straight line, and the products will increase until they get to a straight line. So if you're given a graph like this, you are able to read off that point where equilibrium occurs, because it's as soon as they go straight, as well as the concentrations at equilibrium of your products and your reactants, because it's that point where they're leveled off. So that's what we're going to see in an equilibrium graph. But now, along with equilibrium, that position where the equilibrium is means how much of those products and how much of those reactants we have. And that equilibrium is going to change if we change something in the system. If the system stays the same, equilibrium stays the same. But if we shift something, the equilibrium is going to shift, and that's going to be according to Le Chatelier's principle. So now Le Chatelier's principle says that if one or more factors affecting equilibrium is changed, then the position of the equilibrium will shift in the direction that opposes the change. So I am going to move this equilibrium to the left-hand side or the right-hand side, depending on what I'm going to change in the system. Because whatever I change, I want to shift the equilibrium the opposite way to get back to what I originally had. So if I look at the factors that are going to affect equilibrium, those factors would be concentration, pressure, and temperature. So the first one being concentration. Now, concentration means I'm going to add a whole bunch more of something, or I'm going to remove it. So now, if I say for concentration, maybe I increase a whole bunch of this. So I add more of that. And I increase concentration. So now I have a whole lot of the H2. So in order for me to get back to what I originally had, I need to use this up because I want to now get rid of it because I've added it. So in order to get rid of it, I need to use it up. So I'm going to combine it with that and make more of that. So I'm going to go this way in terms of making that. So if I want to shift there, because now I want more of that to decrease this amount, it means that equilibrium is going to shift to this side to make more of it. So equilibrium shifts to the right, and we are then going to use up all of that hydrogen that we just added. So if I say, what is the effect on equilibrium if I increase the concentration of this H2? I'm going to say the equilibrium will shift to the right to use it up. Okay, and then the same thing can happen if we do vice versa. So now I increase this one. And if I increase this one, I want to use it up to get back to the original that I had. So now to use it up, I'm going to break it down. And then I'm going to shift this way. So I will shift to the left to use it up. Okay, so that's now if we add something. So if I add on this side, I'm going to shift to the right to use it up. And if I add on this side, I'm going to shift to the left to use it up. And then the same applies if I remove something. So now if I remove one of these, like the H or the I2, okay, now I've decreased that pressure and that concentration. So now if I decrease that amount, now I've got less of it. So I want to make more in order for it to be back to what it was. So if I want to make more of it, I'm going to take this and break it down. So I'm going to go this way. So equilibrium will shift to the left. If I decrease that one, I want to make more of it to get back to what it had. So then I'm going to go this way because I'm going to want to make more of it. So if I want to make more, then I'm going to shift to this side. So equilibrium will shift to the right. So if I remove it, if I remove this one, I'm going to shift to the left. And if I remove this one, I'm going to shift to the right. So that's what we say when we're dealing with the Chatelier's principle. And the other thing that you could be asked about affecting these factors is what's going to happen to the yield. So the yield is how much of the products I'm going to make. So your equilibrium is still going to shift one way or the other. And that's going to say either I'm going to increase or I'm going to decrease in how much of those products I'm going to make. So if we look at the other factors, the next one would be pressure. So now pressure is always caused by molecules hitting the sides of a container. So now the more molecules that I have, the more they're going to bounce up and down on the sides of the container, and that means that there's going to be more pressure. If I have less molecules, that means there's less things bouncing on the sides, so there will be less pressure. So now pressure, if I change it, will depend on how many molecules I have on each side of the equation. So if I look at this, the number of moles that you use to balance with, that refers to now my number of molecules that I have. So on this side, I have 2 and 1. So there are 3 moles in particular, or molecules. On this side, I only have 2. So now there is more on this side and less on this side. So now depending on what I do to the pressure, if I increase in pressure, that's going to mean that now I have a lot more pressure. And to get back to what I was, it means then I want to decrease the pressure. So if I increase it, I want to get back to where it was. So you want to decrease it now. So if I want to decrease the pressure to get back to where it was before, I want less molecules, because less molecules is less pressure. So the side with the least amount of molecules gets favored. So in this one, since I have 3 here and 2 here, I want this side. So equilibrium is going to go this way because I'm going to want to make less molecules. So I'm going to shift to the right. If I then decrease the pressure, it's going to mean that I want to increase it because I want to get back to what I was. So if I want to now increase the pressure, it means I want more molecules, because I want more molecules means more pressure. So that means I want this side, because this side has 3 and that side only has 2. So I want to go that way. And if I go that way to make more molecules, that means that I'm going to then shift to the left. So pressure always just depends on the equation that I have. If I have exactly the same molecules on this side and that side, so let's say it was 2 and 2, and I change the pressure, then there's no side that I can favor because there's no side with more or less. So in that case, when we have exactly the same amount of moles on each side, changing the pressure will have no effect on the equilibrium because we have the same number of moles. So you can't choose a side. So as soon as these become the same, pressure won't change this equilibrium. And then if we look at temperature. So now temperature is going to be determined by the enthalpy change. So if I'm given the enthalpy change of an equation, I will always see delta H, and it will either be positive or delta H will be negative. If it's positive, that value, it means that the forward reaction, because the delta H is always from the forward because we go left to right, the positive one means endothermic. So that means the forward reaction likes to take in heat. If delta H is negative, that means that the forward reaction is exothermic. And that means that it will release heat. So if I look at this example, I've now got my HI breaking down into H and I, and the delta H is positive. So that means that the reaction going this way is going to be positive, which means endothermic. And endothermic means takes in heat. Okay, but now that's the forward reaction. So now the backward reaction going this way with the H and the I making HI means I'm going to do the opposite of this. So if the forward one is then plus, the backwards one is then going to mean my delta H is negative, what I had there. Because if I'm doing the reverse, it means I'm going to do the opposite. So now the backward reaction is then going to be exothermic, which means it's going to release heat energy. So now that I know that, because I'm always then going to see what my delta H is, because that will tell me the forward reaction, and then the backward will be opposite. It means depending on what I do to the temperature, now I'm going to favor either the endothermic or the exothermic reaction. So if I say temperature is increased, so an increase in temperature means I've made the situation hotter because I've added heat now and I've increased the temperature. So to get back to what I was, I need to use up the temperature. So if I increase the temperature, I want to use up the heat to decrease the temperature to get back to what I was. So now, to decrease the temperature, I'm going to go to the side that takes in heat, which means I want the endothermic reaction. So that's the forward reaction. So that means that if I want to go forward, I'm going to make more on this side. So I am going to favor the right-hand side because it's endothermic. Okay, so if I increase the temperature to use it up, I'm going to favor the endothermic. And that means that here in this specific example, I'm going to shift to the right-hand side. Okay, obviously now, if this was a different equation, I'm going to have a different delta H, and there I need to find which is the endothermic side to say which side it's going to shift to. Okay, then if my temperature is decreased, that means that I've lowered the amount of heat that I want. So in order to get back to what I have, I am then going to release heat to increase the temperature. So now, if I want to release heat energy to increase to get back to what I was, I'm going to go to the side where I'm going to release heat, being the exothermic. So I'm going to go this way. And that means I'm going to make more of this one, which means the equilibrium will shift to the left because I'm going that way. Because I'm then going to favor the exothermic reaction. So I will always then just find what my delta H is. So if I want the endothermic, I'm going to find delta H plus. And if I want the exothermic, I'm going to find delta H minus. Okay, so each situation is going to be different. So in every question, you are always going to have to look at what you have to know which side it's going to shift to. So if we look at some examples using Le Chatelier's principle, I get given the equation of my ammonium nitrate fertilizer, okay, being manufactured from ammonia. So now I got the equation of 4 NH3 plus 5 O2s gives me 4 NOs plus 6 H2Os. And I'm told that delta H is negative. So that means that the equation going forward is exothermic. Okay, which means that the backward reaction is then going to be endothermic. So then this way is going to be endothermic. So now I'm going to look at this part of that question where it says, what will the effect on the yield of NO in each of the following cases be? So now if I increase the temperature, so increasing the temperature means that I want to decrease to get back to what I was. Okay, so if I want to decrease the temperature, it means I'm going to want the side where I'm going to use up the heat, okay, which means I'm going to want the endothermic reaction. So that means that equilibrium will shift to this side and I'm going to make more of these. So to increase the temperature, okay, according to Le Chatelier's principle, we want to favor the endothermic to decrease the temperature. Okay, which means that the equilibrium is going to shift to the endothermic reaction, which is going to be to the left-hand side. So now if I've shifted to this side, it's going to mean I'm going to make more of these, and I'm going to use those to do it. So the yield of NO, okay, on this side, is going to decrease because I'm going to use it to make those ones. So that means that NO yield will decrease. Okay, obviously in your answer, you write out the words for decrease. So then the next question says, I decrease the applied pressure. So now if I decrease the pressure, to get back to what I want to increase the pressure. So now to increase the pressure, I want more molecules, because more molecules means more pressure. So now I've got to look at the number of moles that I have. So on this side, I have 4 moles and 5 moles. So 4 plus 5 means 9 moles. On this side, I have 4 and 6. And 4 plus 6 means 10 moles. So now, if I want to increase the pressure, it means I want more molecules. So now I look at the side where I'm going to have the most amount of molecules, which means this side. So now I'm going to go this way. So I'm going to shift to the right-hand side. So when I'm decreasing the pressure, okay, to increase pressure, it means I'm going to favor the side with more molecules. So I'm going to shift to the right, because the right-hand side has more molecules. So now shifting to the right means making more on this side, which means that that's the NO, and I'm going to make more of it. So that means that the yield of NO will increase because I'm going to make more. Okay, so those are the kinds of Le Chatelier questions that you're going to get all the time. And you always need to look at the situation. So if we look at a different example, now I have the hydrogen halides, okay, undergoing thermal decomposition, okay, and they give you the equation. And they say the decomposition of HBr is endothermic. So that means that the reaction going this way is going to be positive because it's endothermic. And then state the effect of increasing the temperature on the percentage of HBr that decomposes. Use Le Chatelier's principle to explain. So, increasing the temperature means I'm going to want to decrease that temperature to get back to what it was. So that means to decrease the temperature, I'm going to favor the endothermic reaction. So increasing temperature, so increasing in temp means favoring the endothermic to decrease the temperature, which means I'm going to favor the forward reaction because I'm told that the decomposition is endothermic. Okay, so that means that if we favor the forward, equilibrium is going to shift to this side of the equation, which is then going to be the right. So that means that I'm going to take this and break it down more. So the percentage that decomposes will increase. Because I'm shifting it that way and I'm making more of it. So then another example says that now I've got sulfur trioxide manufactured from sulfur dioxide and oxygen in the contact process. Okay, and they want to know, state and explain how the increase in pressure would affect both the rate of reaction and the yield of SO3. Okay, so now the first part of that, the rate of reaction. So now I know that when I increase pressure, I am going to increase my rate of reaction because increasing pressure means that the molecules are closer to each other so they can react more. Okay, so when I'm dealing with rates of reactions, that's a different situation. Okay, so increasing pressure means that I increase in my rate and it happens faster. But now the yield will depend on my Le Chatelier's principle, because now increasing the pressure means that I want to get back to what I was, so I want to decrease the pressure. And to decrease the pressure, I'm going to favor the side with less moles, because less molecules means less pressure. So to decrease the pressure, I'm going to favor the side with the least amount of molecules. So here I have 2 and 1. So there's 3 molecules in total here and only 2 here. So the least number of molecules means this side is favored, which means so equilibrium will shift to the right. And that means I am going to make more SO3. So the yield of SO3 will increase. Because I'm shifting to the side with the least number of moles. Okay, so then if I look at one more example of this, I've got ammonia manufactured from nitrogen and hydrogen in the Haber process, and you need to state and explain the effect of increasing temperature on the yield of ammonia using the Chatelier's principle. So I'm told that the forward reaction is negative 92, which means going this way is exothermic. So going the opposite way is endothermic. Okay, because the forward reaction is negative, which means then going this way is positive. So now increasing the temperature means that I want to decrease the temperature to get back to what I was. So now to decrease the temperature, I am going to favor the endothermic reaction because I want to use up all the heat. So to decrease the temperature, I'm going to favor the endothermic. And in this case, the endothermic is the backward reaction. Okay, which means that equilibrium is going to shift to the left. And if it shifts to the left, I'm going to take that ammonia and I'm going to break it up. So therefore the yield will decrease. Specifically, the yield of ammonia will decrease. Okay, so that's the kinds of questions that you're going to get about this section, and those are how we're going to answer them.